Chapter 8 is all about solutions. Remember from the very beginning when we talked about mixtures, what's a solution? Nobody's awake yet? Okay. A solution is a homogeneous mixture. In other words, the parts of the mixture retain their own identities. They can be separated by physical means. But a solution is a homogeneous mixture, which means no matter where you sample the solution, you get the same composition of those components, same percentage composition of each of the components. That is a solution. All right. Solutions can come in all shapes and sizes. You can have mixtures of, and this is in terms of what phases can be mixed together. We normally think of a solution as something like, I don't know, sugar water for the hummingbirds. You dissolve a solid in a liquid. That's only one type. Another type that some people indulge in is a liquid in a liquid. Alcoholic beverages, right? They're watered down ethanol. You can have gas in a liquid. A lot of people do indulge in that one. Commonly known as pop. Carbon dioxide dissolved in water is the thing that gives pop its fizz. Gases and gases, right? We're breathing a solution every day, right? Every time you take a deep breath, you're sucking a solution into your lungs, primarily nitrogen and oxygen. Solid, here's one that people don't think of very often. A solid solution, solid and solid. Brass is a good example. Anybody play a musical instrument in high school? Woodwinds? No. Brass? No? Okay. Those instruments are made of solutions. My saxophone's made of a solution of copper and zinc. Think of any others? Let's see, we've covered solid and solid, solid, liquid, 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 gas, liquid, gas, solid, gas and a solid. That one's not there. It would be a gas and a solid. How about shaving cream? That's kind of stretching it. It comes under a different category. We'll get to that in a few minutes. There's Nate. All right. Let me mark him present before I carry on. Mark down as the last lab was turned in. It turned it in. Okay. Which is on me. If I don't find it, then your grade will suffer. Okay. That's my rule. Okay, back to our topics. When we create a solution, we have names, we have identities for the components. There can only be one solvent. And solvent, most of the time, is the major component. You know, by volume or by mass, whichever the case may be, is the major component. You can have any number of solutes. So in sugar water, we start with water and we dump sugar into it. So the major component is water. And the minor component is sugar. But sugar solutions are unique. If you keep putting sugar in water, you'll eventually have more sugar in there than you do water. But since we started out with water as the solvent, we keep it that way. So you can have, I don't know, 90% sucrose. And the industry that uses sugar in large quantities, if they don't need sugar as a solid, it's easier to transport it as a liquid. So they dissolve the sugar in just enough water to make it a liquid, and then they can pump it around. I got a whole book on that topic. So that's by definition solvent and solute. Here's an example. We have water and we're dumping something into it. I'm not sure what that is, but this is a solid and a liquid. And when it goes into solution, you can see right through it. It's may not be fully transparent, right, depending on what you put in there, but it is definitely translucent. And let me see. I don't want to steal my thunder, but I usually do. We're going to talk about, yeah, we talk about it later. So I'll wait. Okay. General properties of solutions. Solutions have to have at least two components, right? It's got to have a solvent and at least one solute. But you can have more solutes, lots more. They can have variable composition. In other words, you can dissolve a little bit of solute in the solvent or a whole lot in the solvent. As long as it all goes into solution, as long as it's all changes into a uniform mixture, a homogeneous mixture, then you can have any amount of solute in that solution. But the properties can change, right? One property would be, let's see, about viscosity. Anybody know what viscosity is? Right. They don't show this commercial anymore. They used to show the commercial with, I think it was Heinz ketchup. Right. They turn the ketchup bottle up like that and wait. I guess describing for the audience just how thick their ketchup is. It would eventually plop out. But if you tried, well, I don't know, if you made tomato soup and you did the same thing, it just all over the place. So you've essentially got tomato components in there, in both of them, but one of them has more than the other. In fact, there are other additions in there, like most ketchup has lots of sugar in it. But it changes the viscosity. Honey is very viscous. I mean, even in warm weather, it runs rather slowly. But if you reduce the amount of sugar, you can dilute honey if you want, and it'll run faster. So the concentration of sugar in the honey determines its viscosity. Those physical properties do change with the concentration of the solute. That's not all of the possible properties. There are chemical and physical properties that can be changed by concentration as well. These solutes are present in the solvent as individual particles. They could be molecules, right? If you make a starch solution, anybody ever made a starch solution? You ever sprayed starch on your clothes when you're ironing them? Right, that's a starch solution. Those are huge molecules, but they're still soluble. Or you could have solutions with just atoms in there. Like when we make a solution of brass, we've got atoms of copper and atoms of zinc, separate atoms. We can make solutions with ions in them. When you dissolve table salt, sodium chloride, in water, it breaks the sodium chloride into individual ions of sodium and chloride ions. But they're individual particles. Now, there is interaction between these particles and the solvent. There has to be. Well, in everything but gases. I should qualify that statement. When you get a mixture of gases, they do interact somewhat, but less than any other types of solutions. Let's see, did somebody else? No, nobody came in. If you take a solution and set it on the tabletop and you seal it so it won't all evaporate and let it sit, you can sit as long as you want. It will never settle out. The solute will never separate itself from the solvent. That's one indicator of a solution. But the solute can be separated from the solvent by physical means. It just depends on what type of solution it is and what the components are. We did something like that with this separating binary mixtures. Remember, we had a sand and a salt mixture, which was heterogeneous. We tried to make it as homogeneous as possible by mixing it up. But there's going to be some variability among the groups with the composition that they determine. But we separated the salt from the sand by dissolving the salt in water. And then how did we get the sand out of it? By physical means. We filtered it. Right? We filtered the sand out of the mixture. That's one physical. That physical separation, filtration, is based upon particle size. If we had tried to filter that through, I don't know, a chain link fence, it wouldn't work because particles are too small. So we used a filter of pore sizes that were small enough to catch the particles. And then what did we do with the filtrate? Sodium chloride solution that ran through the filter. How do we get the sodium chloride back? Nobody remembers? That's too far back. Okay. Evaporation. Right. And evaporation is based upon boiling point. Right. We could remove the water by boiling it, but the temperature is not hot enough to boil sodium chloride. Nowhere near hot enough. Okay, so all these processes of separation are based upon physical properties. Okay, in a homogeneous mixture containing 80 milliliters of water and 20 milliliters of alcohol, identify the solvent and the solute. Right. The major component is the solvent. That would be water. The minor component is the solute, which would be alcohol. All right. I sort of alluded to this problem before when I was talking about concentrations. Concentration of a solute has its limits in most cases. In other words, the solvent, and it depends not just on the solute, but on the solvent as well. The amount of, or the percentage solute that can be contained in the solvent or in the solution is dependent upon the nature of the solute and the solvent. And at some point, most of the time, in fact, even with sugar solutions, you can reach a point where the solvent will not hold any more solute. You've reached the point of saturation. And that's based upon the principle of solubility. How much of the solute, and let's use mass for this discussion. How much of the solute will dissolve in a certain mass of solvent? That's its solubility. There are other expressions, but this is a good starting point. The solubility is the maximum amount of solute that can be dissolved in a certain amount of solvent. And if you exceed that, no more of it will go into solution. Now, this is usually temperature sensitive. And most of the time, if you increase the temperature, you can dissolve more solute in the solvent than at a lower temperature. There are some exceptions that reverses, and we don't really know why. But if you can get more solute in solution by raising the temperature, then you can increase the temperature, dissolve the solute in there, and let the temperature drop back down to room temperature. Just set it on the table, cover it, of course. And what will happen is the excess, as the temperature drops, the excess solute will come out as a solid. If it's a solid and a liquid, it'll do that. Okay. So that's one way to make a saturated solution, is to put more than is soluble at a given temperature, heat the temperature up so it all goes into solution, and then let the temperature drop. Now, there's one catch to that. Let me see. I don't want to steal my thunder again. Yeah, most solids become more soluble in water by increasing the temperature. One catch to that is you can supersaturate the solution. In other words, if it's not disturbed, if you don't have any earthquakes or nobody bumps the jar, then all of that solute may stay in solution even at a lower temperature, but it's very unstable. So all you have to do is just bump the jar or reach in there with your spatula and scratch the inside of the glass beaker, and all that excess will come out of solution. Now, gas solubilities in water are different. They go the other way around. The higher the temperature, the lower the solubility. So illustrate that point. When you put water on the stove to boil, it gets hot. Sometimes you can see the convection currents coming up from the bottom, where the heat is being applied to the bottom. But when you start seeing bubbles come out of that solution, does anybody think that that's water boiling? Nobody's going to commit. It's not. The first bubbles you see coming out of that water are dissolved gases. As you increase the temperature of the water, the solubility of the gases decreases. So as you heat the water up, those dissolved gases, they come out. So by the time water is boiling, there are no gases left in it, right, other than the vaporizing water. Okay. So let's see. Here are solubilities of different salts, right? Ionic compounds in water, and they're dependent upon temperature. Let's see. Lead 2 bromide increases solubility with temperature. Okay. Silver sulfate increases solubility. Copper sulfate increases solubility. Sodium chloride increases solubility, not by much, just a little bit. Silver nitrate increases solubility. Cesium chloride. All of these examples increase solubility from 0 degrees up to 100 degrees Celsius. These are, this is one exception. Calcium acetate becomes less soluble with temperature. In fact, several of the acetates do that. Ammonium acetate, magnesium acetate, they tend to be less soluble. They behave like gases, become less soluble with higher temperature. Well, there's Tyler. What happened to Nate? Oh, he's still here. Okay, let me mark Tyler. Chris. Oops. Are they individually? Okay, yeah, there's some extras okay. Okay. Up here. Okay. What effect does pressure have on solubility? Well, if you're trying to dissolve a solid in a liquid, a solid in a solid, a liquid in a liquid, then pressure has no effect on solubility. The way they state here, solids and liquids, there's no effect. And we seem to be focusing on water, which is fine, right? Because most of what we do is in aqueous solutions anyway, so focusing on water as a solvent is perfectly all right. Pressure has no effect on solids and liquids in water, but the pressure of a gas will increase. As you increase the pressure on the gas, the solubility of the gas in water increases in a major way. In fact, there's a law that governs that called Henry's Law. And what it says is, if you want to know the concentration of the gas in the liquid, you want to know the concentration of the gas, then all you need to know is the pressure, and there's some constant. Okay? So if we wrote that like we were writing our gas equations before, where we said, let's see, parallel to this would be like volume and temperature. Volume and temperature, Charles' law, is a constant. Okay? If we keep this constant on one side and move that pressure over here, then the concentration is proportional to the pressure. What that means is, as the pressure goes up, concentration has to go up in order for this to remain constant. Now they say Henry's constant, but I've never used Henry's constant. I always used it in the modified version like we did with our gas laws. If you say that's equal to that, and then this is equal to that, then this condition here and this conditions here, they're equal to the same constant. So this one's equal to that one, just like our gas laws. So if you know 3 of these, you can solve for the 4th one. There is a Henry's constant, but I would be willing to bet that it's dependent upon the units of measure. Okay. Now this P, it could be, if there's only one solute and one solvent, say it's water, for instance, and we have this one gas, then P would be the total pressure. But if we have a mixture and we have to invoke Dalton's law of partial pressures, then this pressure would be specific for one of the gases in that mixture. So it would be, the solubility would change differently for each of the gases in that mixture. Okay. All right. So I mentioned this one earlier, saturated solution. It's a solution in which the solvent is holding the maximum amount of solute that it can at a given temperature. So one way to also know, right, let's take off from where we left when I was telling you how to create a saturated solution. If that beaker sitting on your desk has solid in it at room temperature, then it's saturated. If there's no solid, then you can't tell if it's saturated. Right? If you know how it's prepared, like I've prepared saturated sodium chloride solutions, table salt, for an experiment. And I would create the saturated solution, like I said before, and have that solid on the bottom. And then I would just run it through a filter. And I know the solution is saturated, but there are no solids left in it. So it's ready to use with an experiment where you're going to create solids, perhaps. But what's happening? We can see on the macroscopic level that that solid in the bottom is not changing in amount. Right? It stays stationary. But on the microscopic level, you got your solution and you got your solid down here. These atoms, ions, molecules, whatever the case may be, are going into solution and returning to solution, and going into solution and returning to the solid at the same rate. And if you could get small enough to watch them do that, it would be happening too fast for you to see. This is what I mentioned earlier, the supersaturated solution. If you heat up a solution and get all the solute dissolved in it, and you know in advance that the solute is going to be more than that solution can hold at room temperature, then when you let it cool to room temperature, if it has not precipitated, if it doesn't give you any solid as a result, then you know it's supersaturated. And like I said before, it's extremely unstable. It doesn't take much. I mean, you just look at it cross-eyed and the solid will drop out of solution. Okay. Anything that's not saturated is unsaturated. That's a simple definition, qualitative definition. Most solutions fall into this category. We also have other descriptive terms. When we say a concentrated solution, that's one in which the solute is relatively high and approaching saturation. A dilute solution is anything that has where the solute is very low in concentration. So those are general terms, and the quantitative values that are associated with these vary depending on the nature of the solution. One way to concentrate a solution from a dilute solution, if you want to go that way, is remove solvent, right? Sometimes it's easy to do, sometimes it's not so easy to do. If you've got a solute that is non-volatile, then you can just sit it out on a bench or even heat it and remove the solvent, just like we did with our sodium chloride solution. And sometimes you can see the concentration effect, right? In this case, the one on the right is dilute, the one on the left, where we've removed solvent over time by just letting it evaporate, becomes bluer because you've got more of those blue forming molecules in a smaller volume. So it looks bluer. In fact, we can use that to our advantage. Have you guys in MLT done anything with optical density yet? No, that comes later. You haven't done any chemistry much at all, have you? Next semester? Okay.
We're working on solutions and solutions.
Okay. One way to determine the concentration of a solute in a solution is to shine a light through it and measure the intensity of light on this side and the intensity of light on that side and ratio them. So when you get to that point, remember Beer's law. Okay, if you haven't already heard of it, you'll hear of it again probably.
Yeah, we've done a little bit of that with our H and H's when we're trying to find the hematocrit and
Oh,
the hemoglobin.
okay. So you have used it. Don't remember hearing the word Beers? Okay. Yeah. Yeah. Not Beard's law or beer drinking law. Beer was a person. Okay. You can actually, if the particles are small enough, you don't actually have to have a solution to use this optical density ratio. In fact, I think some instrumentation will give you the concentration of red blood cells, for instance, in a sample by measuring the difference in light transmission. Okay, aqueous solutions, obviously the solvent is water. And when we have an aqueous solution, we use AQ in parentheses, like for sodium chloride, for instance, would be like that. We use the compound that's in solution and then we say what it is. It's aqueous solution. Non-aqueous solution just means that it's a different solvent than water. And we're not going to mess with those. They're used extensively in organic chemistry. And just in a word, the reason that they don't use water in a lot of organic chemistry reactions is water can be a reactant and it can interfere with the reaction they're trying to process. So they use non-aqueous solvents. Okay, how does the temperature and pressure affect the solubility of gas in water? Well, as the temperature decreases, gas solubility increases, or vice versa. That's why, well, when I used to drink pop, I kind of got away from it. But I never liked to open a 2-liter pop bottle that was right off the grocer's shelf, right at room temperature. If you do that, open it like that, it goes, you lose a lot of the fizz because at those elevated temperatures, carbon dioxide is less soluble. The only reason it's still in there is because it's under pressure. But if we invoke Henry's law and decrease the pressure by uncapping it, then the amount of carbon dioxide in solution decreases. So what I like to do is take my 2-liter pop bottles and shove them in the refrigerator for a couple of hours, get them cold. Then the carbon dioxide will stay in solution when I crack it, and it'll just go. I mean, that's half the fun of drinking pop, right? The fizz, right? Tickles your nose when you drink it. It even settles your stomach too. But that's another topic. We'll talk about buffers then. Have y'all talked about buffers in MLT yet? I'm sorry? What was that?
There's a buffy code in the board.
A buffering code?
No. BUFF.
A Buffy code? I never heard of that one. That must be particular to your discipline. Yeah. It's not a vampire slayer, is it? No, I'm joking. As in Buffy the.
Yeah, I get it.
Okay, for a solute to dissolve in a solvent. This is the way we rationalize, we visualize the solution of a solute in a solvent. It's a 3-part process. So you got the solute over here, and you got the solvent over here. It could be anything, But in order for the solute to get ready to go into solution, you've got to break any intermolecular bonds between the solute. So we have to add energy and break bonds. Actually, not break intramolecular bonds, but break intermolecular bonds. In other words, those bonds that are holding the molecules together, they'd be fairly strong in a solid, a little bit weaker in a liquid, and almost non-existent in a gas. But you have to break those bonds first. So this is an endothermic process. You have to add energy to get those particles apart. You have to do the same thing for the solid, right? So it's endothermic as well. Sometimes we call this make a hole. Right, you got to get those solvent molecules apart so there's some place to fit these guys. Okay, so up to this point, we've added energy, and we've added energy to get them apart. Well, when you put them together, right, then what you get in this solution is an exothermic process. Right? Because you're forming a bond. I mean, you're moving to a lower state, an energy state, because the interactions now are bringing them together, and that is a lower energy state, so we have to give up energy. Right? So we've got endothermic, endothermic, exothermic. Okay, so let me put it in the terms that your authors had. These intermolecular forces are solute-solute bonds. These are solvent-solvent bonds. And these are solute-solid bonds. Okay. Now, when you put, let's be specific. When you dissolve a solid in water, sometimes it gets hot and sometimes it gets cold. Right? If you've ever been in a hospital room and you needed a hot pack for a pulled muscle, say, or you can do it at home too. It's not exclusive to hospitals, but they use both types of packs. They have this bag of water, and it's got a little capsule in it, and you break it and shake it and dissolve it, right? If it's a hot pack, it'll get hot, right? If it's a cold pack, it'll get cold. Okay, so if you got a headache or you got a fever they want to bring down quicker, you can put these cold packs all over you and bring your temperature down. Well, the reason it happens that way is a balance between these two and this one. See, I want to keep it, this is step one, this is step two, and this is step three. Step 1 and 2 are endothermic, you got to put energy in. 3 is exothermic, you get energy back. So if step 3 gives you more energy back than you put in these two steps, then the balance is heat evolved, excess heat. Exothermic is greater than endothermic plus endothermic. But if we put more energy in, endothermic and endothermic here, then we get back here, then that pack is going to be cold. All right? Think you can explain that on a test? Or at least pick it out of a multiple choice. Okay. So what are some of the factors that affect how fast the solution forms? Okay. Up to this point, we've talked about equilibrium conditions. In other words, how much will go into solution? What's the solubility? That's an equilibrium situation. You can wait as long as you want, or as long as required for the solute to go into solution. It could take a few seconds. It could take minutes or hours. It could take years, depending on the solvent and the solute. But what increases the speed? The rate at which the solution forms. Well, first of all, particle size, right? Because these processes occur at the surface of the particle. In other words, if we have sodium chloride, right? Sodium chloride's a cube. I mentioned that before, didn't I? Spill salt on the tabletop and look at a magnifying glass. You have little bitty cubes. If this is sodium chloride cube, then it goes into solution from the surface, right? And when sodium and chlorine or sodium and chloride ions leave the surface, that exposes fresh surface underneath. So the speed at which this happens depends upon the particle size, surface area. So if you have a certain mass of sodium chloride and it's a big chunk like that, you've got a fixed surface area on that one big cube. But if you break it into smaller cubes, you're actually, for that mass, you're increasing the surface area. And that will increase the rate of solution. All right, so that's number one, particle size. Agitation also increases the speed of solution. Why is that? Well, if we look at this cube again, right? Think of it on the microscopic scale. Right? If you've got water here, and sodium chloride here, then what happens if this is completely still, calm? Then as these sodium and chloride ions leave the surface, they don't just automatically move to the far ends and make room for everybody else. They kind of hang around the surface. They produce a local zone of increased concentration, right? And that hinders the ability of water to get in there and attract those ions. And so that local buildup of that microzone of increased concentration impedes the solution of that large particle. So what happens when you mix it? Well, when you mix it, as soon as these guys go into solution, sodium and chloride go into solution, then we're moving them away. And fresh exposure to water molecules increases. So the rate of solution will also increase with agitation. Okay? Temperature, right? Most solids will form aqueous solutions at a faster rate if the temperature increases. Right? If we use water that's boiling, it's at 100 degrees or pretty close, then that solid will go into solution much faster. The reason for that is kinetic energy. Right? If we need to add energy to get those ions apart and add energy to get those water molecules apart, remember step 1 and 2, then more energy will do that for us. And these, as we increase the energy, those water molecules are just, they're zipping along and they smack into the surface and it adds energy to everybody. So you can get them apart. That will speed up the reaction. The other effect is probably a little more difficult to understand. It's called the common ion effect. The common ion effect is a hindrance to forming a solution. In other words, if you try to put sodium chloride in solution, but you've already got sodium and chloride ions in the solution, say we try to put more salt into a saltwater solution, it's not going to happen very fast, because there are already sodium and chlorides out here and you're approaching solubility limit. Right? So the common ion effect actually impedes the dissolution of the of the salt in the aqueous solution. So those four factors are the major factors to consider for solution rates. Okay, we've got some rules that are helpful to determine whether or not you can actually form a solution, or whether the solution is going to be have a low solubility limit or a high solubility limit. And it has to do with polarity. When you consider the polarity of the molecules in the solvent and the solute, and this comes under the heading of polarity. Let's see, we have talked about polarity, haven't we? Molecules have slightly negative sides, slightly positive sides. Okay, just check it. So, if both the, if both the solute and the solvent are polar, and there are varying degrees of polarity there also. But if they're polar, then what you have is a molecule that is slightly positive one end, slightly negative on the other end, and the solvent, if it's also slightly, let's put the negative on the top of this one, slightly positive on the bottom, then when they approach one another, the strength of attraction is increased because you get this positive negative. It's purely electrostatic. So if both the solute and the solvent are polar, you're very likely to get a solution formed. What if one of them is nonpolar? Say, like that. Say that's a nonpolar molecule and this is a polar solvent. You're less likely to get a solution. Because there's no place for them to attract. But if both of them are nonpolar, then you're more likely to get a solution there. So that's where this rule of thumb comes from, that like dissolves like. Like means polarity. If they're both polar, solutions favored. If they're both nonpolar, solutions favored. And this is, like I said, a rule of thumb. So it's not absolute. And some ionic solids are not soluble in water to any great extent. I think, didn't I give you a solubility chart at some time in the past? Let's see. It would have been in the review document, probably. Let me check to be sure. Oh, no, it's not there. Well, let me show you what it looks like. Are we going to get it in a second? No, I don't see it. Okay. See if I got a copy. Solubility. Maybe I didn't give you one because you're not going to need to. Here we go. I give you one that looks like that. Yeah. Okay. That's our solubility chart. Make a copy. This works for ionic compounds So you got a cation and an anion for aqueous solutions. So all you have to do is find the cation across the top and then the anion down the left and follow them until they meet and see if that square is grayed out. If it's grayed out, then for all intents and purposes, that solid is not soluble in water to any great extent. Now, if this were general chemistry course, you'd eventually discover that they are slightly soluble, and you learn how to calculate how soluble. But you're probably glad you're not in that class. Anyway, there are rules governing solubility, and this chart is based upon those rules. Let's see, these are some of the rules. If you have a group 1A compound where the cation is lithium, sodium, potassium, rubidium, cesium, those compounds are all soluble, every one of them, without exception. Any ammonium compounds where you have that complex ion, ammonium, NH4 plus, with any anion, those are all soluble also. All the acetates are soluble. Like C2H3O2. If we put a hydrogen in front of acetate, what do we get? Acetic acid, right? Vinegar. But you can also put other cations there. Doesn't have to be hydrogen. It could be sodium, it could be calcium, magnesium. Any of those are soluble. Nitrates, NO3 minus. Any cation with a nitrate is soluble. Now we get to some exceptions. Most of the chlorides, bromides, and iodides, in other words, the halogens as anions, when you put a cation with them, most of those are soluble except for silver, lead 2 plus, and mercury, mercury 1 plus. Remember, mercury is that oddball. Mercury is always 2 plus charge. But if you have two of them together with a 2 plus, that means this one has all the charge itself, whereas this one only has 1 plus for each of the mercuries. Okay? All right. So that mercury right there is a 1 plus charge. Those are not soluble with chlorine, bromine, iodine. Sulfates. All the sulfates are soluble except for these: calcium, strontium, barium, right? Beryllium and magnesium, the alkaline earths, they're soluble sulfates. But calcium, strontium, barium are not soluble. Silver sulfate, lead 2 plus sulfate, they're not soluble. And those are all taken into account in this chart. Plus, the rules are down here at the bottom, too, if you're interested. If you were studying to be, like, if you're going for a BS in chemistry, you probably want to memorize those rules. But since you're not, I just pulled up this chart and we used the chart instead. Now, question just occurred to me. All right, the exam for this section doesn't have that chart in it. So if you need the chart, all you have to do is ask. Or you can bring it to the test, since you have a copy of it. Or you can use, if you take it online, like if you're sick that day and you need to take it online, then you can use that chart. You can use periodic table too. Other insoluble compounds. Carbonates are generally insoluble except for the ones with ammonium, like calcium carbonate. What's calcium carbonate? Tums, right? Anybody ever eat Tums? You're eating calcium carbonate, ground up limestone. You know you're eating rocks. Well, ladies, you probably know about putting rocks on your face, ground up into fine powder. It's called makeup. But everybody at one time or another has eaten limestone to settle their stomachs. Phosphates, right? All the phosphates are insoluble except for the ammonium compounds and the 1A ions. I should have said that earlier also. Those lithium, sodium, potassium, rubidium, cesium, those are all soluble regardless of what they're connected with. Sulfides, they're insoluble except for the ammoniums, the alkali metals, and calcium, strontium, barium. Right, so those alkaline earths are also soluble. And the hydroxides. Sodium hydroxide is infinitely soluble. That's otherwise known as Drano. Right? You ever use Drano to unclog a drain? That's sodium hydroxide. Right? That's why you don't want to get it on you, because it'll burn. Okay, so let's moving on. These are the rules, and all of those rules are at the bottom of this page. The rules are set up 1 through 7 in a particular order. So if you have a compound where you can apply 2 or more of these rules, the one that takes precedence is the one above with the lowest numerical value. So if you've got a battle between 1 and 4, 1 wins. Okay. All right. Oh, there it is. How come it wasn't in here? I'm sorry? Yeah, but it's not in this slide set. Oh, there it is. 2 pages stuck together. Okay, good. So it's being recorded. That's what I was interested in. All right. So if there's a greater difference, the larger, I said like dissolves like, but there's also a fine nuance to that. If the solute and solvent polarity results, if the difference in polarity are wide, the wider they are, the less likely they are to be soluble. So if something is definitely nonpolar and something is definitely ionic or very polar, then they're not going to be soluble at all. So it's a decrease in solubility when their polarities are radically different from one another. When their polarities are close to one another, then they're more likely to be soluble. And there's a whole 2 or 3 slide discussion that I go through with my general chemistry class to try to describe that. But since we do this in one semester, we don't have time. Moving on. So let's see. Which of the following, this is a practical application to see if anybody was paying attention. Which of the following ions are generally soluble in water, form compounds with lead 2+? So the lead 2+ is the cation, and we're looking at anions here to see which one of these would be soluble in water. Right? We could throw E out all. That's I don't know, just a filler, right? You don't form compounds with 2 cations. So we throw out sodium. Then we look at the others. So we find lead 2+, which is way over here on the right-hand side. And we go down, looking at each one. Sulfide, it's grayed out. Chloride, it's grayed out. Nitrate, it's clear. So lead 2 nitrate is soluble. Sulfate, yep, sulfate's grayed out. So the nitrate is the only one that's soluble out of that bunch as a lead 2+ nitrate compound. Okay, how do we express? We mentioned earlier, or I mentioned earlier, that concentrations of these homogeneous mixtures can change. the composition, we need to figure out how to express that concentration so that we can use it in calculations, use it in chemistries. So we're going to look at the most common ways of expressing concentrations. The most common two ways of expressing concentrations is percent concentration by mass. Actually, percent by whatever we define. Remember, percent is a dimensionless number. It just means parts per hundred. So that's why it's so dangerous. When somebody says percent, you need to ask them, what do you mean by that? Right? Is it mass per volume? Is it mass per mass? Or is it volume per volume? Right? When you go to, some states have state-run liquor stores, and they're the only ones that can sell product. Right? And they call them ABV stores because ABV stands for alcohol by volume, which means it's percent ethanol in the product based upon volume of ethanol for volume of the booze. Okay. But when a chemist is analyzing a solution, very often they'll express it as mass, like mass of the solute per mass of the solution. So percent is very tricky. You got to know how the expression is expected to be was produced. Actually, molarity is the other one. Molarity is very common, and we'll talk about that in a second. Molality is another one that is very useful, but I'm not sure. I don't think we're gonna. Let's see. Oh, yes, we are. In fact, our next lab, we're going to use molality. So before you leave, be sure and get a copy of Molar Mass by Freezing Point Depression. Okay, we'll talk about all three of those coming up. Okay, well, I already talked about that one. The Achilles heel of percent is its dimensionless number. Percent by mass. So when we express the concentration of a solute in a solution, we do it by mass of the solute divided by mass of the solution. So the total mass of the solution, which would be what? They don't make that distinction here in, well, yeah, they do in right below it. So this left a marker somewhere. What did I do with it? I lose more markers that way. Percent, and well, usually it'll be expressed like this: percent, mass, mass. And for solutions, what we're saying is the mass of the solute divided by the mass of the solution, which is also mass of the solute plus the mass of the solvent times 100, because it's percent. So when you're calculating these things, don't forget to put the mass of the solute down here in the denominator too. What's the percent by mass? If we dissolve 5.5 grams of glucose in 78.2 grams of water. Well, this would be 5.5 grams, wouldn't it? This would also be 5.5 grams. And then this would be 78.2, was it? Times 100. Okay. So that's the thinking part. Crunch the numbers and you should get 6.6%. By mass, mass. Percent by volume. It's similar. And we would change this to a V. So the volumes, just like the masses, have to be in the same units of measure. Right? You can't put grams up here and kilograms down here. It'll be the same units. So we would have there. Now, the trick to this one is to actually know what the volume of the solution is, because let's go back to think of that 1, 2, 3 step. When you make a hole in the solvent to put your solute in, maybe it fills up the hole and maybe it doesn't. Maybe it shrinks back down. Right? So the volume of the solvent may not be the arithmetic summation of the volume of the solute before and the solvent before. The volume of the solution after could be less or it could be more than you expect. So that actually has to be measured. And so this is the volume of the solute, and this is the volume of the solution. We cannot say add one plus the other. Now, sometimes I do it if it doesn't have to be real accurate. It's just ballpark, then I'll go that route. But technically speaking, you have to know the volume of the solvent in order to do this calculation. Excuse me. All right. Okay, I should look at my own slides, right? I see some puzzled looks on your face. What in the hell is he talking about? So this is the volume of the solvent. Actually, I've seen it both ways. So what type of problem would this present? If you've got the volume of solute is, say, 60 milliliters, right? 60 milliliters. And the volume of solvent is 60 milliliters. Your percent solute is 100%. And in fact, if we break the rules and say, let this be the smaller amount and this is a larger amount, then you can have more than 100% by that method. Whereas if you have the one that I started out earlier, where you have the volume of the solution, you'll never exceed 100%, not without errors. Okay. So using their method, volume percent of a solute in 30 milliliters of methyl alcohol, enough water to give 435 milliliters of solution. Well, now they're switching. I wonder if that's supposed to be, that should be solution. There's your copy. That should be changed. Actually, that should be solution. Right? I made a note, but I didn't change the slide. Okay. Rather than solvent, it should be solution. Right here. And the reason I know that is because this problem works it that way. 435 milliliters of solution is in the denominator. 30 milliliters of methyl alcohol is in the numerator times 100. And that should give you 6.90% alcohol by volume. I'm sorry? I'm sorry, my hearing's pretty bad. Oh, okay. Okay. Do you use booze as an example? Let's see. 30 and 435, 30 and 435. You know, there's another problem. Notice this exercise is methyl alcohol in this slide, and it changed to ethyl alcohol in this slide. But it's the same type of calculation. 6.9%. Let's see. That's not very strong, is it? That's just above beer. Let's see. There for a while, there were laws all over the country that beer couldn't have more than 3.2% alcohol by volume. And then most of them did away with that. And now it can be 6.4%. So this is a little bit higher than beer. What's most, let's see, wines vary all over the place, right? Most vintage type wines are in the neighborhood of 15%, 18%. You can get some, what do they call them? Pop or fruity wines. They can go down to like 10%. And then the hard stuff, right? It can be 45%, like 90 proof.
What was
Everclear, it should be 100%. Yeah. Yeah, should be 100%. And it's difficult to make ethanol at 100%. Pure, if you distill it, you're a moonshiner, you're distilling your mash, the highest amount of alcohol by volume you can get is 95% with 5% water. That's it. What happens is, as the concentration drops, then you start to form what's called an azeotrope of alcohol with water. So they come off together at a different temperature. So as the temperature increases, you start getting more and more and more ethanol water combination coming off. So you can never get better than 95%. So what they did in the past was they added benzene. Benzene forms a different azeotrope with ethanol and water. Comes off at a different temperature, at a lower temperature, actually. Yeah, I believe it's a lower temperature. And that gets rid of all the water, and then the rest that comes off is ethanol. You get 100% that way. Now, the way I used to do it, well, we would buy 100% from the manufacturer. But you can also take 95% if it's not denatured, right? That ethanol we have in our stockroom is denatured. They put something else in it. I forget what, but it makes up a significant portion of that other 5%. And if you try to drink it, it'll make you sick. It won't kill you, it'll just make you sick. So they denature it. So I think so that they don't tax it. Right? If it's Everclear, that type of stuff, you got to have that tax strap over the bottle. But the way I would do it was I would filter it through sodium sulfate, anhydrous sodium sulfate solid. And sodium sulfate is very hygroscopic. It'll take up that 5% water, and what would come out was 100%. Or if I'd had some sitting around for a while, right, the cap wasn't really tight, it will suck up water from the atmosphere. So I would just run it through sodium sulfate to be sure it was completely water-free, dry. All right, you probably have heard enough of that already, so let's move on. Now, I didn't have to worry about sodium sulfate being dissolved in alcohol, because alcohol is only slightly polar, and sodium sulfate is ionic. So I didn't contaminate my ethanol by doing that. Okay, mass volume percent. Similar to before, we need to know the volume of the solution, and we need to know the mass of the solute. So that would be percent mass volume. See it written like that. Okay. If you have these values, say you have, let's use an example. Since we're on mass by volume, 25%. we have 25% sucrose, right? Mass volume. What does that mean? That means 25 grams of sucrose in 100 milliliters of water. And remember, whenever you have a ratio like this, you got a conversion factor. So if we know that value, and say we have 50 milliliters of solution, then the milliliters cancel, right? We multiply them together. And that gives us what, half? Right? So half of that value would be 12 and a half. That means if I have 50 milliliters of this solution, I've got 12 and a half grams of sucrose in the volume I extracted. Anytime you have an equivalence, you've got a conversion factor. Anytime you have a ratio given to you, it's also a conversion factor. Okay, mass percent concentration of 10% contains 10 grams in every 100 gram sample. So it'd be 10 grams of solute, it's either A or C, per 100 gram solution and 90 grams of solvent. That would be the one, because it would be a total of 100 grams. All right. How many grams of sodium chloride are needed to prepare 150 milliliters of 0.9% mass volume sodium chloride? Okay. So let's see. Well, that's too messy. Let's just do it fresh. So we want 0.9%, 0.9% mass volume of sodium chloride in 150 milliliters of solution. So if we've got that, we need a conversion factor that will get rid of the milliliters of solution and leave us with grams of sodium chloride. All right, so the ratio here is grams per milliliter, per 100 milliliters. So this is 0.9 grams per 100 milliliters, because this is percent, right? Parts per 100. Okay. So 100, that's 1.5 times 0.9, right? And 4 9 13. 13.5 grams. Let's see if I got it right. Nope, I missed it somehow. Oh, 2 decimals over. Yeah, 1.35 grams. Okay, molarity. Molarity is very, very useful expression of concentration. Have y'all done molarity yet? Yeah, okay, so we don't have to spend a lot of time on it. It's got, the abbreviation is a big M, just a single M. We can do that because there's nothing in the periodic table, it's just a single M. That's good news. And it's moles of solute per liter of solution, by definition. And notice what we've got here. We've got a formula. Molarity equals moles per volume. So if you know 2 of these, you can solve for the third one. It's just, if you use this formula, the volume has to be in liters. All right. Let's say you have 1 mole of sugar in 125 milliliters of solution. So 1 mole of sugar in 125 milliliters. How many liters is that? Well, you can do it 2 ways. Excuse me. You can use conversion factor, Right, you know the conversion factor. Puts milliliters on the bottom, liters on the top. So we have 1,000 milliliters per liter. So you divide that by 1,000 and you get 0.125. Well, if you do this a lot, you know that this milli equals 10 to the minus third. So 125 times 10 to the minus third. That's 3 positions. 1, 2, 3. So that's how many liters we're talking about here. 0.125 into 1 milliliter, 1 mole. Should be 8 molar. Now we did that one. That one's really simple because we could do it all in one step. But show me a balance that measures in moles. They don't exist. You'd have to convert that 1 mole to grams using the molar mass of sucrose and then measuring out that many grams on your balance before you could make this solution. All right. So you have a 10 molar sugar solution. What volume of this solution do you need to have 2 moles of sugar? You see, how am I doing on time? Might make it. So we've got 10 molar solution. And that equals moles divided by volume. What do we have? We do have moles. Moles. And we want to find out volume. So you just solve for the unknown, right? So that's 2 divided by 10, which is 1/5 or 0.2. Let's see, 3. And that's liters. We have 0.2 liters of solution. How many milliliters is that? Try 200. There you go. Okay. Get a little more complicated. The purpose of this slide is to show you the difference when you're using molarity of 2 different compounds in aqueous solution. If they have the same molarity, then it's going to require different masses of each one. But if it's the same mass, it's going to give you different molarities. Right, so we've got 100 grams each of sodium hydroxide and potassium chloride. Yeah, potassium chloride, 100 grams. Okay, and they're both going into separate solutions, 250 milliliters each. Right. What's the concentration of each one in molarity? Right. So we have to convert these masses to moles. We need the molar mass of sodium hydroxide, grams per mole, and we need the molar mass of potassium chloride. Okay, so how about sodium? That's 23, isn't it? Yeah, 23.00. Oxygen 16, hydrogen's 1.01. So we get 1, 0, let's see, 7, 10, and 40. So it's 40.01 divided into 100. I get 2.499. 2.499 moles of sodium hydroxide. Okay. How about this one? Potassium chloride. What's potassium? Let's see. 39.10. Rounded off. And I got chlorine memorized. It's 35, 45, 5, 5, 15, 74.55. divided into 100 is 1.34, 1.341. Close enough. That's how many moles of potassium chloride. All right. So we're going to put those each in the same volume, separate solutions, but in the same volume. How many liters is 250 milliliters? You got to do that in your head. 0.2500 liters. Okay. So let's see. I'm going to do this one first since it's sitting right here. 0.25 divided. It's 5 point. Let's see. We've got 4. Yeah. 4 significant figures. Oh, wait a minute. Yeah, 4. 5.366 molar. And then 2.499 divided by 0.25 is 9.997 molar. I think the slide rounds it off though. Yeah. They round this one off to 10. And round that one off to 5.37. But you can see with the same masses, different compounds will give you different molarities. All right. Now let's talk about dilution. You guys talked about dilution and yeah, you mentioned that before. Yeah, you're doing dilutions. What type of dilutions are you doing? Okay. You've done that, right? Have you done dilution of concentrated solutions to dilute solutions? That's what this is talking about. Okay. When I was working in soil science at LSU in Baton Rouge, we would have to do, hundreds of soil analyses a day. And to make up the correct concentrations of our solutions for extracting the soils would have taken quite a couple of hours in the morning just to make those solutions. So what we would do was we'd make up a stock solution that is more concentrated and keep it in a smaller volume. And then when we got ready to do the analyses, we dilute some of the concentrated solution to an amount of working solution that was sufficient to do all of our analyses. So, and we use this method. Let's see, best way to describe it is if we have a stock solution over here of a molarity that's, we're going to call it concentrated molarity. But we want a diluted molarity over here. So we're going to use a volumetric flask. Right? And it's marked to contain a specific volume. And so if you fill it up with an aqueous solution up to that mark, you know that you have the volume of that particular flask. Let's keep it simple. Let's say it's 1 liter. And so up to that mark, this flask will contain 1 liter of solution. So we're going to take some of this out. We're going to take a volume of this one, a volume of the concentrated, and we're going to deliver that volume into here. Now the volume of the dilute is this total volume, right? Volume of the dilute there. Right? We want a diluted molarity on this one. So it's going to be a lower value than this one because we're going to add more solvent. we're going to take only a portion of this one here, put it in here, and then bring it up to volume with the solvent. So we're diluting the solute. All right, what do these have in common? Well, first of all, let's look at the expression. Molarity equals moles per volume. If we solve for moles, we get molarity times volume. Okay? So here, if I take out a certain volume at this molarity, then the number of moles of the concentrated equals the molarity of the concentrated times the volume of the concentrated. That's how many moles I took out, right, on my way over here. Right? If we have this volume times that molarity, we have the moles of the dilute. Okay? So far? What do they have in common? When you take out some of this solution and put it over here, did the moles change? No, you pulled out a certain number of moles of solute here, put the same number of moles over here. So this ND, this NC, try it again. This NC equals ND. It's the same number of moles we pulled out as we put in. So if we substitute the concentrated times its volume and the dilute times its volume, there's our formula. Sometimes we say M1V1 equals M2V2. That's the formula we use. So if we have, if we know we want a certain concentration here, and we know the volume of our container, and we know the molarity of the concentrated solution here, right? So that's this one, and this one. We solve for what volume I need to take out of that one and put over here. That's the dilution of that. Questions? No. Okay. How would you prepare 100 milliliters, 0.9% saline solution in water from a 10% saline solution? All right, so we did it for molarity, but it works for these other concentrations also. All right, if we have, we want to prepare 100 milliliters of solution that is 0.9%, 0.9%. So this is the concentrated of our dilute, and this is the volume of our dilute. Okay. From a 10% saline solution. So the concentrated solution is 10%. And we want to know volume of concentrated that we want to put into that 100 milliliters. So we can use that same formula. Right, in this case, where instead of molarity, we're using concentrated. Dilute. And like dilute, we want to solve for this one. And just plug in our values, right? As long as the units are the same for the concentration and the milliliters, it's going to be value for this one because they're ratios. All right, so we got 0.9% and the volume is 100 milliliters. Did it have an extra zero on it? No, it didn't. And divided by 10%. Right, so the percents cancel. Even though they're dimensionless numbers, we can, for our purposes, that's perfectly all right. 1/10 of this would be 10, 9/10 would be 90. Divided by 10. So it should be 9 milliliters. 9 milliliters dissolved in 100 milliliters. Oh, I didn't realize it was animated. Oh, I see. Diluted plus 91 milliliters. All right, so if this is the volume, 9 milliliters we need, then we only need 91 milliliters of water. Now, that's assuming that the volume is proportional to the masses. If it's not, if the volume changes as we add stuff to it, then that wouldn't be right. But it's going to be close. Why'd they pick 0.9% saline? No ideas? No, 0.9%. 0.9% saline solution is isotonic to your body fluids. They didn't teach you that? Okay. Now, you don't want to, as a general rule, unless you're pressed and the person's dying, you don't want to put 0.9% sodium chloride in their system for very long. It might be isotonic, but you're going to overload their kidneys, especially with chloride. So that's why instead of sodium chloride solutions in the hospital, they use lactated ringers, which is gentler on the system, but it's still isotonic. All right. Oops. Oh, no, we're still dilution. We're supposed to start the lab at 11, right? I think. 10:55. Okay, so I got to get moving here. Let's see how much more I have to go. Yeah, I'll tell you what, I'm going to skip this one. There's the answer. So if you look at the video, you'll at least have the description and the answer to the problem. Minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters, 0.8. This is simply M1V1 equals M2V2. What you need to do in order to solve these problems is to set it up concentrated, dilute, dilute. And be sure you get your numbers in the right place. Once you got your numbers in the right place, you know where your unknown is, and then you can use the formula. If you just try to do it, from memory, you're likely to make a mistake and put numbers in the wrong place. All right, so the answer should be 60 milliliters in this case. All right. I mentioned earlier that solutions have characteristics that are different than suspensions. You have a suspension, first of all, the suspended particles are going to settle over time. And that's what you saw when you put that sand, sodium chloride mixture in solution. The sand just dropped right out. All right, that's a suspension. The solution was the sodium chloride dissolved in water. So you had two types. You had a homogeneous mixture and you had a heterogeneous mixture. Well, there's one class of mixtures that mimics a solution. It's called a colloid. Now, remember that 1, 2, 3 step we did before? This doesn't work for colloids because the particles are too big and they don't dissolve in the solution. So they don't obey those rules or that scenario. What a colloid does do is it will once you get a colloid, a dispersed phase in a dispersing medium. So the dispersed phase is the identifier for what we would think of as a solute. The dispersing phase would be similar to the solvent. The dispersed phase, once it gets dispersed, it will remain dispersed, just like a solution. It won't settle out. But it does not form a solution because it's not going into those holes that we've formed in the solvent in that earlier description. Right? There are no holes for it to go into. The reason it stays suspended, and colloids are essentially suspensions. The reason it stays suspended is the particle sizes are so small that the kinetic energy of the dispersing medium is enough to keep them suspended. Right? That on the microscopic level, those dispersed phase particles are getting smacked by the dispersing medium particles, right, from all directions, and it keeps them suspended. All right. Now, how do we tell the difference? That's where we use the Tyndall effect. The Tyndall effect, I assume it was named after Tyndall, is a light scattering property. So when you have a solution and you shine a light through it, say we have a solution here, and you shine a bright light through it, right? Then, and you position your eyeball on this side, you can see the light beam coming out. Okay, that's true for solutions and for colloids. But if you look at the right angles, so I'm going to draw it down here, but if your eyeball is out here, if it's a solution, you won't see anything, nothing. There's no scattering of the light. So it looks like it comes in this end, it comes out the other side, and you can't see it go through. But if it's a colloid, there is light scattering with those particles, and you can see the beam. Right? You can see the beam in the solution for a colloid. That's the Tyndall effect. It's essentially light scattering of the light beam. All right, here's an example. The container on the left is a solution. We can't see the beam, but the container on the right is a colloid. And you can readily see the beam there. Right? Now, who cares, right? Well, when you're driving down the road at 4 o'clock in the morning and you run through a fog patch, you're going to see light scattering. Your beams, your light beams are going to bounce off the particles in that fog, and fog is a colloid. It's a liquid in a gas colloid. So it matters then. That's why so many of the modern cars now have built-in fog lamps, right? Lights that are positioned down low. And if the feedback to your sensors in your car is high enough, and you have them properly set in your controls, then your bright beams will automatically dim and the fog lamps will come on. Okay. So now we've moved from solvents to colloids, suspensions. Suspensions are heterogeneous mixtures that are not uniform throughout. Right? And we saw that with our sand suspensions. And they will settle. Right? They can settle just setting them out on the bench. Gravity will pull those larger particles down. Or if the particles are really small and you want to get them out of suspension quicker, you can stick them in a centrifuge. and simulate gravity. Right. Okay, so this table comes straight out of your textbook. And it describes those characteristics of and differences between solutions, colloidal dispersions, and suspensions. So it's kind of a continuum, so to speak. I'm not going to spend any time on it. We've already talked about that stuff already. So a colloidal dispersion is all of these. It contains small particles not visible to the naked eye. It's a mixture that contains particles that don't settle out under the influence of gravity. Now I wonder, if you put a colloid in a centrifuge and spun it fast enough, you think it would settle out? I bet it would. I bet it would if you increase the G forces to, I don't know, some centrifuges will easily go to 1,000 Gs. If you go up that high, I bet you could get the colloid to separate. Does everybody like Jell-O? Some people do and some people don't. Jell-O is a colloid. Right? It's a protein, an animal-based protein dissolved in water with sugar and flavorings. So they get that protein from animal bones and hooves, parts of the animal that, you know, they normally throw away. They just boil the protein out of it and make your Jell-O. Now you really don't like it. That's why, what's the saying? You don't want to know what they put in your hot dogs.
I've never liked Jell-O, but I really don't like it now.
Okay. Okay. Now we're going to talk about colligative properties of solutions. And this is very important because you're going to use one of these colligative properties in next week's lab, molar mass by freezing point depression. Freezing point depression is a colligative property. Well, I say that just offhand, but what does I mean by colligative? Colligative property is a physical property of a solution, and it only depends upon the concentration of the solute. It doesn't matter what the solute is. Concentration is the only thing that matters. Of course, the colligative property, the magnitude and the way the colligative property responds to various changes depends also on the solvent. But as the concentration of the solute changes, it has an effect on this colligative property that's independent of its identity. So if you had 1 molar sodium chloride dissolved in water versus let's see, that wouldn't be right. Sodium chloride would split. So half molar sodium chloride and 1 molar sucrose would give you the same colligative property in water relative to freezing point changes, boiling point changes. Right? Anybody ever wondered why your ice cream freezer, you have to put all that salt in there with the ice? Makes it colder. Right? You dissolve all that sodium chloride in water and it lowers the freezing point of water. Right? It lowers it so low that it's low enough to freeze custard when you're churning it. That's one colligative property. Freezing point depression. That's the one we're going to use next week. Another one is boiling point elevation. Right? If you put a lot of salt in water and try to boil it on the stove, it's going to take longer to get there because the boiling point of water with a lot of salt in is a lot higher. So boiling point elevation is also a colligative property. And it doesn't matter that it's sodium chloride. You could use anything else. if the molar concentration of the of whatever the solute is the same, then the boiling point elevation is going to be the same. The change in temperature from the pure boiling point of the solvent to the solution boiling point. That's the difference, that delta T. That's what we're focused on. Let's see. Vapor pressure. We talked about vapor pressure, didn't we? You put a liquid in a closed container and cap it. Eventually, it'll build up a pressure inside the container. And you can measure that. Yeah, but I know we did that. So, and the vapor pressure will change depending on how much of the solute there is in solution. In fact, as we increase the amount of solute in the solvent, the vapor pressure decreases. Osmotic pressure. Everybody know what osmotic pressure is? It's a difference. What you have to have is a membrane that's semi-permeable. It only allows water to pass. And if one side, for instance, is pure solvent and the other side has some solute in it, then you get a differential movement of water from the pure solvent into the solution. And you can measure that as a difference in pressure between the two. That's osmotic pressure. That's the problem with solutions that are either hypertonic or hypotonic if you give them to your patient. If you set up an IV with either a hypertonic or a hypotonic solution, you'll eventually kill them. First thing it'll do is if it's hypotonic, it'll cause the red blood cells to rupture, explode. If it's hypertonic, it'll cause the red blood cells to crenate, just shrivel up. And that's due to the osmotic pressure. The cell membrane is the barrier. And if you've got more water on the outside than inside, it moves in, causes the cell to go like that until it reaches its stress limit and explodes. Or if it's lower concentration of water on the outside, then the water will move from inside the cell out, and the cell will just shrivel up. Same result. Your patient's dead. Okay. Let's talk about vapor pressure first. Ooh. All right. I'm out of time. It's going to take some time to cover this. Boyle's law is not a difficult lab, so I think I'll be okay if I maybe take another half hour to finish this. Rayleigh law. Don't need that. Rayleigh's law describes the change in vapor pressure for solutions that have non-volatile solvents, like sodium chloride solution. If your solution has ethanol in it, if it's booze, then there's a modification to Rayleigh's law, and it still works. But this form of Rayleigh's law works for solvents that are non-volatile, like ionic solids. So the vapor pressure of the solution can be calculated if we know the mole fraction of the solvent and the vapor pressure of the pure solvent. Okay, and we put a little zero up here. So remember what have we talked about mole fraction? Yeah, we've talked about mole fraction. Yeah. So you need to know the mole fraction of the solvent. So if you're given the mole fraction of the solute, say the solute is 0.1, right? Mole fraction, then what's the mole fraction of the solvent? 0.9, right? 0.9, because they both have to add up to 1. So this would be a value. Then we know the vapor pressure of the pure solvent. This times that, since it's going to be less than 1, gives you a decreased value for the solution vapor pressure. That's Rayleigh's law.
Leave. Can I do something with the lab online?
You can get the data from your partner.
She writes it.
Oh. Okay. Well, actually, here, we've only got enough equipment for 4 groups, right? So at least 2 groups are going to have to combine, right? So, okay. So get yours from group 5 and you can finish your lab that way. All right, that's vapor pressure. Yeah, that's good right there. So here's the explanation for a change in vapor pressure. If you have the pure liquid, you've got molecules leaving the surface and evaporating into that headspace and creating a pressure. So the weaker the forces holding those molecules in the liquid, the higher the vapor pressure. So things like ether, that is very low intermolecular attraction, is going to have a very high head pressure, whereas water is going to have a low vapor pressure because the molecules are very strongly attracted to one another. Well, when you put a non-volatile solute in there, it does 2 things. One is all this happens at the surface of the liquid. So those yellow spheres are showing you that what we've done is we're decreasing the surface area at the molecular air level. So fewer of those molecules are being evaporated. Also, since those solute molecules are in solution, we know that there is intermolecular attractions between the solute molecules and the solvent. So they're also holding those molecules back. So those 2 effects reduce the vapor pressure on the solution as compared to the pure solvent. Boiling point elevation. All right, that's the next colligative property. Boiling point elevation. Okay. Notice that what we're interested in is the change in temperature. That is the absolute difference between pure solvent boiling point and the solution boiling point. Now, in the past, delta T, I've always said final temperature minus initial temperature, and that's still true. But for these formulas that we're going to present with delta T's, you only need the number, not the sign. So you could do it either way, subtract either way and get the right number. This delta T is an absolute difference between the pure boiling point and the solution boiling point. And when you got that, it's going to be equal to some constant, this boiling point elevation constant, which is particular for the solvent. So it'll be a different value for the solvent, whether it's water, or in our case, well, we're not using that one for next, but this has to be given to you, or you have to look it up in a reference manual. And then this value is the molality of the solute. Okay, we didn't describe molality in detail like we did molarity, but it's similar to molarity. Remember, molarity is moles per liter of solution. Right? Molality is still moles, and this is solute per kilogram of solid. Okay, so this is a volume of the whole solution. This is kilogram of the solid. Now, why are we doing that? Why do we need this and not that? Because our colligative properties are forcing us to look at change in temperature. What happens to volume when you change the temperature? The volume changes, right? We can't have that. We can't let the volume change in our calculation, right? That would be, you're trying to hit a moving target. It'll never stop. So instead of that, we use mass. So moles of solute per mass of solvent, kilograms of solvent, is the value that we use here. All right. Now, when standard temperature and pressure are used, standard conditions actually, standard temperature and pressure for everything except gas equations. Temperature is 25 degrees C. Pressure is 1 atmosphere, just like before. And concentrations are all 1 molar. So under standard conditions, temperature, pressure, and concentration are these values, in case you're ever presented with that in the future. All right, this is the one we're going to be using next week. Freezing point. Let's erase all of that. I'll leave that there. This is freezing point depression. So our absolute change in temperature is now equal to some K freezing point for the solvent. And if it's the same solvent as the boiling point, it's still going to be a different K. Right? It has to be empirically determined. And then the molality of the solute is figured the same way as before. Okay, so how can we use that to determine the molar mass of the solute? Well, if you substitute in here, this instead of that, substitute moles of solute per kilogram of solvent. Now we know that all we need is this value given to you, right? It won't be water. Right? We're going to use organic system. And how do you get delta T? Well, you need to determine the freezing point of your solvent, or your pure solvent, right? That's one value. T of the solvent. Then you need the T of the solution, right? And that gives you your delta T. And if there's a sign, you just take the absolute value. And that goes in here. This is known, right? And we've got one unknown, molality, right? So we can solve this equation for molality. Now we know the number of moles per kilogram of solvent. How do we get the number of moles of solute? We know how much solvent we put in there, right? We weigh it. So now we can find out how many moles of solute, right? That gives us moles of solute. So molecular weight, remember, molar mass is mass per mole, right? So that gives us this one. How do we know the mass of the solute? Because we measured it when we made the solution, right? So we measured both of these, measured that one ahead of time. We measured this one when we put those two together, and then we calculated that one, we can calculate the molar mass of whatever the solute is. All right. All right. One more. Remember which one that was? Osmotic pressure. Osmosis. Right. We've got a lab coming up. Let's see. It's after this one. It's osmosis and dialysis. That's a fun lab. But I'm going to make the distinction now. A semi-permeable membrane, by definition, is one that only allows water to pass, or small, very small molecules like gas molecules. Right? But for our purposes, water is our defining solvent. So a semi-permeable allows water to pass. A selectively permeable is usually based upon particle size. Right? So you could let simple sugars go through and starches would stay behind, for instance, because they're a lot bigger molecules. So that's the difference between semi-permeable and selectively permeable. Now, what do we mean by osmosis? Well, I mean osmotic pressure. I've already explained what osmosis was, and it's movement across a membrane in response to a difference in concentrations on either side of the membrane. So for a semi-permeable membrane, in our example, right, the higher concentration is inside the tube. So the only thing that can move is water. So what happens is the water tries to move across the membrane to try to equilibrate the two solutions to the same concentration. Trouble is, there are forces at work that are trying to keep that water where it is. Now, in the beginning, water wins. It moves into that tube. But eventually, as the height of the column rises, it exerts an opposing force, an opposing pressure, the osmotic pressure, that keeps the water moving backwards. So across that membrane, right, if you've got pure, we're going to stick to water here, and solution on this side, then water is going to try to move that way. But at the microscopic level, what's happening is water's going this way and water's going that way. But since there's more water on this side than there is on this side wins eventually. I mean, in the beginning, water moves this way more than it moves that way. So we start building up pressure here. Well, when we do that, that puts pressure on the membrane so that more water molecules go that way. And eventually you reach an equilibrium where they're moving the same rate backwards and forwards. And it's all due to that added pressure. So as this one builds up to that and this one goes down there, this difference in pressure supplies the force that equilibrates everything. Okay, this is what it looks like on a molecular scale. Now, you can also drive the movement of water backwards. All you need is an artificial pressure here on this side. And for practical purposes, it's very high, like hundreds of atmospheres. But as you increase the pressure, you favor the movement of water that direction. So you can take seawater and drive it under pressure past a semi-permeable membrane and get drinkable pure water out the other side. There are some places on the planet, but that's the only way people can get the drinkable water. They live close to the ocean. They got plenty of cheap energy. So I'm thinking of the Middle East. those Arab countries that have lots of oil. Right? They can produce electricity for pennies. And they can use this process to produce drinkable water. Reverse osmosis. All right. This is an interesting problem. I'm going to go through it pretty quick. It occurred to me a long time ago when I was about that high that these tall trees, when I first heard about the sequoias in California, I said, these guys are 300, 350 feet tall. How do you get water up there? Right? Those leaves have to have water, right? So the first assumption I made was that, well, I don't know. I don't see anything pushing it from below. I couldn't see it then. So I said, well, maybe it's pulling the water up, right? Because I knew water had adhesive forces. So maybe as the water evaporates from the leaves, right, it creates this pull. You evaporate water and produce this air bubble inside the leaf, and then it tries to fill it, and it pulls like that. But it turns out other experiments decided that no, they proved that that doesn't happen. So we're back to the push. So what could push water 350 feet to the top of a sequoia? Well, as it turns out, osmotic pressure can do it. We've measured the osmotic pressure inside the xylem of roots of these trees at 20 atmospheres. That's a huge difference in pressure. Well, is that enough to push water all the way to the top? Well, let's see. Say it's only 300 feet tall, not 350. So if we take 3 feet and we convert that to millimeters, then that's the first step. This is how tall the tree is in millimeters. Why did I do millimeters? Because we're going to change pressure into millimeters. So 20 atmospheres gives me so many millimeters of mercury, but this is water. So I use this value here to convert it to millimeters of water. Right? That's the pressure, the height of the column that would be under pressure for 20 atmospheres in the roots. And it turns out that that column would be 2 times 10 to the 5th millimeters high of water, whereas the tree is only 9 times 10 to the 4th millimeters tall. So yeah, there's more than twice the available pressure to push water all the way to the top. So that explains why those tall trees can get water way up there in the top. Osmotic pressure does it all. Now, when we express the concentration, we can start with molarity and calculate osmolarity. Now, why is that different? Well, since the difference in pressure across this membrane is due to the concentration of particles, if you dissolve sugar, right, glucose, for instance, glucose goes into solution and does not dissociate. What that means is if you know the concentration beforehand, you know the concentration after. Right? It's 1-to-1. But if you put sodium chloride in there, what does sodium chloride do? It produces 2 particles for every 1. So if you have 1 molar sodium chloride, when you put it in solution and calculate its effect on the osmotic pressure, it's twice that amount because you get 2 particles for every 1. Calcium chloride. Right? What would calcium chloride do? It would produce 3 particles. For every 1 mole of that, you get 3 moles of particles. Right? That's why calcium chloride is a much more effective ice melter than sodium chloride. Sodium chloride is a lot cheaper, right? That's why the road crews use it. But if you want to put something on your sidewalk that'll melt the ice quicker and more effectively at lower temperature, then calcium chloride is a better choice. So when you go in the Walmart and buy this bag of, I think it's got this big red letters on it called heat. You buy that stuff, look on the bag, see what it's got in it. Sometimes it's a mixture of calcium chloride and sodium chloride. Sometimes it's pure calcium chloride. It's going to be expensive, of course, but it's much more effective at melting ice than sodium chloride. Plus, there's one other benefit. If your walkway is made of concrete cement, don't put sodium chloride on it. It'll pit holes in it. Sodium replaces the calcium, and that's not structurally sound. It gets washed away, and you got holes. Next spring, you got holes in your concrete. Well, I can't use that example here. Do we have any concrete out around the building? Concrete walkways? Check it to see if it's got holes in it. Got pits in it. That means they've been using sodium chloride in the winter. If it doesn't, then somebody's smart enough to buy calcium chloride. There's a building right next to ours next to New River, the Irma Bird Center. If I know about them. I walk around them 3 times a week, and I walk over this concrete. It's got holes everywhere. They've been using sodium chloride on their concrete. Well, okay, so the expression here is if you have 1 molar aqueous sodium chloride, then in osmotic terms, that's equivalent to 2 molar. Well, actually, 2 osmolarity. So when we, and that factor here is 2, and the factor here is 3. That's given a little I. So when we write the formula for freezing point depression, right? We've got our K value, and we've got our molality. If the solute dissociates in solution and it makes 2 particles for every 1, then the I would be 2. So we put the I here. That's all you need to make that formula useful for dissociating solutes. Okay, so osmolarity for 3 molar sodium chloride is 2 times 6 osmol. All right. I'm not going to spend a lot of time on this because we know hypotonic means that the is referring to the tonicity of the solution. In other words, hypotonic means that it is produces a lower osmotic pressure than within the cell. The solution does. So what that does is it causes the water to move into the cell. Yeah. Always think in terms of water movement. And hypertonic causes water to move out of the cell. Okay. Isotonic means the pressure is the same, water doesn't move at all. Right. And I described this one earlier. This is what you get in various situations. The normal cells are going to look like discs with depressions in the middle. And if the solution is hypertonic, you're going to get crenation there in the middle. If it's hypotonic, you're going to get an exploded cell. Now, EMTs, rather than using 0.9% sodium chloride, they will have available 5% mass volume glucose. Now, what they have to be careful with is, are they dealing with a diabetic, right, on the way to the hospital? If that person's a diabetic and they start feeding them 5% glucose, they're going to be dead before they get there. They're going to go into diabetic shock. So they have to be sure that that's not the problem. And I'm sure they have alternate solutions that can be used that are a little easier on the person. But you have to, there are trade-offs, right? If your person is, if your patient is bleeding out, right, or has lost a lot of blood, you got to replace those fluids before the heart shuts down. So sometimes the trade-off is you got to give them the glucose even though they're diabetic, because otherwise they're going to die anyway. So I wouldn't want to be in their shoes. And they call it D5W, dextrose 5% by weight. That's what D5W means. And dextrose is 6 carbon sugars, right? Most often it's glucose, but it could be any other 6 carbon sugar mixed in there with it. All right. Let's see. I've already gone too far, so I'm gonna skip over this one. If you want to read more about this one, how problematic 0.9% sodium chloride is on your body, then I've got this link down here that describes, right, how you're stressing your kidneys with extra sodium and extra chloride. All right, there's an isotonic solution. Osmolarity is you multiply the molarity times the number of dissociated particles, and you get the osmolat. We're going to have to skip this too because I'm running out of time. All right, well, that one's animated, so that's good. There we go. And there we go. Okay. So at least, is this one animated too? No, it's not.